the next and last new concept we'll look at before we move on to get us ready for chapter 17 is going to be about phase. So let's start with our equation for a traveling wave. D equals A times sine kx minus omega t plus phi naught. This is familiar from when we looked at one-dimensional waves on strings. This part of the expression right here, this is called the phase. That phase has a symbol of a phi. This constant right here, that's called the phase constant. Okay, so the whole thing is the phase. This part at the end is the phase constant, and both things are in radians. So if we're thinking about phases, there are a couple of places in a wave where we would recognize the phase right off the bat. So let's say this is a picture of a traveling wave. So here's the height of the wave as a function of horizontal position. Let's say that this picture is taken at time t. So this is a snapshot graph. If we looked at this point right here the phase is equal to pi over 2. And at this point, if we put in pi over 2 here for our equation, we would see that d is equal to a maximum, it's equal to the amplitude. At this point on the wave, the phase is equal to 0. If we put in a phase of 0, we get our height of our wave is equal to 0. And down here on this part of the wave, the phase is equal to minus pi over 2. If we put in minus pi over 2 for our phase, then we get that the height of the wave is minus the amplitude. Okay, those are some parts we know. What we often care about when we're doing an interference problem in particular, we care about something called the phase difference. So let's get a definition of phase difference. So phase difference because it's a difference, we're going to call it delta phi. And delta phi is exactly what it sounds like. It's the difference in phase between 2 points on a wave. Oops, 2 points on wave. So let's just pick any 2 points. Let's call this point point number 1, and let's call this point point number 2. So our phase difference, delta phi then, would be phi 2, so the phase of point 2, take away the phase of point 1. If we were at one of these 3 points, we would know right off the bat what to put in for our phase, but we're not at one of those 3 points, so what do we put in for our phase? Well, we put in this expression for our phase. So the phase at point 2 is k, put brackets around this just so we really are clear what we're doing, k times position 2, take away omega, the angular frequency times time, plus the phase constant phi naught. Then we take away our phase of point 1, k times x1 minus omega t plus phi naught. So just to clarify here, try and head off any questions that you might be wondering about. Because this is a snapshot graph, these are both the same times. These 2 phases are referencing 2 different points on one single wave. So the phase constant, phi naught, is the same for both because they both mean this wave, and this wave has a certain phase constant. They both have the same wave number k, so no matter where we are on this wave, we have the same wavelength. So wave number, 2 pi over wavelength, is the same. And omega would also be the same. So the only thing that's different between these 2 points is where we are horizontally. So that's where these things are coming from, and we know it's the same. So let's just write these guys out. So we have k times x2, take away x1. So right here I multiplied my k into x2 minus k x1, then I took my k outside. Then I've got minus omega t. Over here I have minus times minus omega t to get plus omega t. And here I have plus phi naught. Here I have minus phi naught. So then that leaves us with k times delta x, where delta x is the distance along the x-axis here. So our phase difference between 2 points on a single wave, delta phi, is equal to the wave number k, which is 2 pi over lambda, times the spatial difference, delta x. That's important enough to put in a box. Okay, so this tends to be a tricky concept, which is why it's nice to introduce it in Chapter 16 before we come back and we start using it heavily in Chapter 17. Make sure you really understand what's going on here, because it will start to come a bit faster in Chapter 17. So before we move on and do some examples, let's look at a couple of special cases. So let's look at this one first. So let's call this guy case 1. And in case 1, we're going to look at what is the phase difference between two crests of a wave. So we're going to look from crest to crest. So that means I'm going to pick this as my point 1, and I'm going to pick this as my point 2. And I'm going to try and find the phase difference. You might be able to just see this in your head, which is fine, but after we see what the phase difference is here, we'll make a general result as well. So my phase difference, delta phi, is 2 pi over lambda times delta x. And our delta x in this case is the horizontal distance between points 1 and 2. Distance from crest to crest is a wavelength. So we've got 2 pi over lambda times lambda, and this would be true had we picked trough to trough as well. 2 pi over lambda times pi leaves us with 2 pi. So now the extension is, what if I hadn't picked the distance point 2 as this one? What if I'd picked point 2 as this one? So if I went from this crest to this crest, now my delta x would be 2 lambda. So if I put in 2 lambda here, I'd get 4 pi. Then what if I went to the next crest? I'd have 3 lambda. And then for my answer, 2 pi over lambda times 3 lambda, I would get 6 pi. So our general result, if we're looking at 2 points that are at exactly the same phase, so they're both at crests, then our delta phi is equal to 2 pi, or 4 pi, or 6 pi, and so on. When we have something where the phase difference is an even multiple of 2 pi, these things are called in phase. And this happens when 2 points are at the same point in cycle. Okay, so that's one extreme. We looked at 2 places in exactly the same point in the cycle. What if we picked 2 places that were at exact opposite points in the cycle? So our case 2 will have 1 point as a crest and 1 point as a trough. So I'm going to label this my point 2, and I'm going to label this my point 1. So if I want to find my delta phi, then delta phi is equal to 2 pi over lambda times delta x. What is my delta x? So from here to here, as we go from a crest to a trough, this is delta x, and this is the same as a half of a wavelength. So we have 2 pi over lambda times lambda over 2 gives us pi. So to extend to different points in the cycle, what if this were point 1 and this were point 2? Then I would have a delta x equals 1 1/2 wavelengths. And if I put in 1 1/2 lambda here, I would get 3 pi here. I could go to the next crest and I'd have a difference of 2 1/2 wavelengths. If I put 2 1/2 lambda here, I'd get 5 pi for my phase difference. So my next special result is that if delta phi is equal to pi, or 3 pi, or 5 pi, and so on, so all of the odd multiples of pi, those are called out of phase. And this is terminology we're going to use pretty liberally. So these two wave points are out of phase. That means they're at opposite points in the cycle. Okay, so once you're content that you're pretty happy with that and you understand what it's talking about, next we'll move on and we'll do some examples. For this example, let's look at a spherical wave. Let's say it's traveling outwards from a point source. So this example might be a light bulb that we turn on, and the light waves travel outwards from that source. What is the phase difference between the 2 points on the wave marked with these dots? So the first thing we have to get at is a little tiny bit of notation. For one-dimensional waves, delta phi, we said, was 2 pi over lambda times delta x. So there's the expression we use when we're waves along a line, so one dimension. If we're in 2 dimensions, however, or 3 dimensions, so these would be our circular waves and our spherical waves, so 2D and 3D waves, there, instead of using x, we use r, where r means the distance from the source. Okay, so we're trying to find the phase difference. We have a spherical wave, so we're going to use this expression. We'll use r instead of x. We have 2 pi over lambda. We don't know lambda, so let's not panic about that just yet. Let's sort out our delta r first, and then we'll see how that works out with our lambda. So let's come to our picture and ask, what is this picture telling us? Remember that for spherical waves, the lines represent the shells or the crests. They're the wave fronts. So everywhere we have a line, it's a crest. In between any two lines is a trough. So the lines represent the crests. In between two crests is a trough. So here are 2 points that we have. So this is point 1. Point 1 is on a crest. Let's call this guy point 2. Point 2 is in between 2 crests, so point 2 is on a trough. This is going to help us figure out how to find it. So what else do we know about these pictures? Well, we know that the distance between any 2 crests is equivalent to a wavelength. So from here to here is lambda, from here to here is lambda, and from here to here is lambda. Okay, and that comes back from when we discussed these waves. So let's put in our distances, r1 and r2. So r2, let's call this one point 2, just because I want this one to be bigger. Let's call this point 2 and call this one point 1. So r2 is the distance from the source to point 2. So there's r2 is from here to here. From here to here is a wavelength. From here to here is a wavelength. So from here to here, which is r2, that's equal to 2 times the wavelength. Okay, hopefully that's clear. So we go source to crest. In between this guy is lambda, this guy is lambda, so the whole distance is 2 times lambda. Okay, so my point 1 has r1 from the source to my point. From here to here is 1 full wavelength, so from crest to crest. From here to here, the crest to a trough is equal to a half of a wavelength. So from here to here, that's our distance r1. That's lambda plus lambda over 2, so that's 1 1/2 lambda. So now we have expressions for R1 and R2 that we can put in our equation over here, and we can use that to find our phase difference delta phi. So we have 2 pi over lambda. Delta R is R2 minus R1. 2 pi over lambda. R2 is 2 times lambda. I'm going to subtract R1, which is 1.5 times lambda. So 2 pi over lambda. 2 minus 1.5 gives us a half. We see that lambdas cancel and 2's cancel, and we're left with pi. This answer shouldn't be a surprise at all, because you probably notice that this guy's on a crest, this guy's on a trough, so they're out of phase. And we know that for wave points that are out of phase at exactly opposite points, the phase difference is an odd multiple of pi. Okay, one more example and we'll be able to clue up with this section. So in this last example, we have a 100 hertz sound wave, and it's traveling with a wave speed of 343 meters per second. So sound waves are spherical waves. If we drew the full picture, there'd be big spherical crests here as the sound went from the speaker to the person's ear. I only selected a small portion of that picture because otherwise it would mess up the whole slide. Okay, so my frequency is 100 hertz. My wave speed is 343 meters per second. And question A asks, what is the phase difference between 2 points on the wave that are 60 centimeters apart? So what I know is that my difference in space, my difference in distance, is 60 centimeters or 0.600 meters. Okay, part A says find the phase difference. So let's write down our equation for phase difference. So phase difference delta phi is 2 pi over lambda times delta r. In this one, delta r is easy, we know that, but what is lambda? Well, we know v equals f lambda, so lambda is v over f, 343 meters per second, divided by 100 hertz, where hertz is seconds to the minus 1, gives us a wavelength of 3.43 meters. So let's put in that lambda with our delta r. We've got 2 pi divided by 3.43 meters times delta r, which was 60 centimeters, 0.600 meters. When we put that through the calculator, we get 1.10. Would be okay to leave it as 1.10. Might be better to put in radians, just as a reminder that these difference in phase angles are in radians. And the reason we do that, oh, let's see, one more comment. It's 1.10, so it's not a multiple of 2 pi, and it's not an odd multiple of pi. That tells us that for these 2 points, they're not exactly in phase or out of phase, they're somewhere in between, and that's going to happen lots of times. So not everything is going to be exactly in or out of phase. Okay, last, little bit of a trick question. How far apart are 2 points whose phase difference differs by 90 degrees? So here it says that the phase difference is 90 degrees, but we have to remember to use radians. And 90 degrees is pi over 2 radians. So we're going to try and find delta r if our phase difference is pi over 2. So let's put in our equation, 2 pi over lambda times delta r, and let's solve for delta r. So delta r is going to be pi over 2 times lambda over 2 pi. We see here that our pi's will cancel, and we're left with lambda over 4, 3.43 meters divided by 4 to get 0.858 meters. If we take stock of this answer, then it pretty much makes sense. 90 degrees is a quarter of a cycle, so it makes sense to think that our difference in distance is also going to be a quarter of a cycle or a quarter of a wavelength.